Polymers in nanomedicine. For a drug to be effective after it has entered our body, it needs to reach the target site where it is intended to work and still be at the correct dosage. In some cases, this can be difficult, as the drugs can be degraded by the harsh environment in the body, not get to the correct site, or not be absorbed properly. These things can cause the drug not to be effective or even become toxic. One of the solutions to this problem is the use of nanomedicine. Nanomedicine in drug delivery uses amphiphilic block copolymers. A copolymer is a polymer made of more than one monomer unit, and in a block copolymer, these different monomers are arranged in precisely defined segments, or blocks, joined together. They are amphiphilic and so have a hydrophilic and hydrophobic region. So the copolymer is made of hydrophobic blocks joined to hydrophilic blocks. When added to water, these amphiphilic block copolymers self-assemble to form micelles, spherical structures with the hydrophilic sections arranged on the outside and the hydrophobic sections forming a core in the middle. A drug can then be held inside these micelles. To show how these micelles are formed and can be used to treat disease, we can look at a specific example of the drug haloperidol. Haloperidol is an antipsychotic drug used to treat schizophrenia, and so its target site is in the brain. However, in the body there is something called the blood-brain barrier, which prevents some molecules, including haloperidol, from passing in the blood into the brain. Therefore, when the drug is taken on its own, dissolved in the blood, not much of it will reach the target site in the brain. This means traditionally much higher doses of the drug are given to make it more effective, leading to many unwanted side effects. The solution to this is to hold the haloperidol molecules in micelles so they can pass the blood-brain barrier and then be released. One amphiphilic block copolymer used for making the micelle is called Pluronic 85, and it has this structure, with one hydrophobic and two hydrophilic sections. The hydrophilic polymer used is polyethylene oxide. This is formed from a type of chain growth polymerization called anionic polymerization. In the initiation step, the monomer, ethylene oxide, is attacked by a nucleophile, opening the ring and forming an anionic polymer chain. This then goes on to do propagation, attacking another ethylene oxide monomer, which is added to the chain. This process continues until all the monomer has been used up, forming the polyethylene oxide polymer, which is still reactive. The hydrophobic polymer used is polypropylene oxide, which is made by the same anionic polymerization mechanism as before. To make the Pluronic 85 block copolymer, the nucleophile and ethylene oxide monomer is added first. As it is a living polymerization, the chains of polyethylene oxide are formed at the same rate, and so it makes chains of equal length. This continues until all the monomer is used up, when the ends of the chains are still reactive. At this point, the propylene oxide monomers are added, which form the polypropylene oxide block. Again, the ends of these chains are still reactive when all the monomers are used up, at which point more ethylene oxide monomers are added to form the final hydrophilic section. When added to water, the hydrophobic blocks form a core in the middle of the micelle, and the hydrophilic blocks point away and form a shell. Haloperidol is a hydrophobic molecule and so is held in the core of the micelle. It can now be effectively delivered to its target site in the brain, passing the blood-brain barrier in the micelles. Polyethylene oxide is the most commonly used hydrophilic polymer because it has a flexible linear chain and the ends of the chains can be modified easily by using a specific initiator. Another advantage is that it does not aggregate in the body or in storage due to steric repulsion. However, a potential issue with its use is that it has been shown at times to cause a specific immune response, where antibodies have been made against it in the body. This can cause the polymer and therefore the micelle to be destroyed in the body, reducing the effectiveness. In more serious cases, it can even cause an allergic reaction. To avoid this in the future, self-antigens, markers telling the immune system not to attack it, could be added to the micelles. Furthermore, both polypropylene oxide and polyethylene oxide are non-biodegradable, which means they will not break down in the body. This can be a problem, as after they have been used to deliver the drug, they can accumulate in the body, potentially causing side effects. Alternative polymers, for example polyesters for the hydrophobic blocks, could be used in future. Despite some concerns, studies still show that the use of the Pluronic 85 copolymer for delivering haloperidol increases the concentration of the drug that reaches the brain and therefore its effectiveness. Thank you for watching.